Hey guys, BuildZoid here, and today we're going to be taking a look at the PCB of the RX 9070 Swift OC from XFX. I bought this card, so a big thank you to the channel supporters for funding the purchase of this GPU. If you would like to support the channel, there are links in the description that you could check out. That would be very much appreciated. And before we get into this, a quick disclaimer. This is not a review, and I am not an engineer. I'm just some guy on the internet who really likes looking at PCBs and reading documentation. So, yeah, that's that. And with that out of the way, let's get into it. Starting off with the latest addition to AMD GPUs, shunt resistors that are actually connected to something that monitors the voltage drop across them. Because very technically, on Vega 64 and Vega 56 reference PCBs, you do have shunt resistors. They're just not connected to any kind of monitoring circuitry, so they don't add any functionality to those cards. But on the RX 9000 series, you get shunt resistors for each of your 8 pins, and also you get a shunt resistor for the PCIe slot. If you have a 12-volt high power connector, you get shunt resistors or a shunt resistor for that, depending on the card. But yeah, so basically you get a shunt resistor for every single 12-volt power input for these GPUs. And those shunt resistors are then monitored by 3 different shunt monitoring chips that I unfortunately don't know what they are, because the labels on these are not like search engine friendly. I tried searching what they are, I couldn't come up with anything. So yeah, but these are the shunt monitoring chips. So for the PCIe, like the 2 8 pins over here, it's U5521 and U5524. And then for the shunt on the PCIe slot, the monitoring chip is on the back of the card, and it's U5522. So thanks to these shunts and the associated monitoring chips, AMD GPUs now have software power readings that are comparable to NVIDIA GPUs. Because this has actually kind of been a problem with AMD GPUs, is that depending on what card you're looking at, the software power readings will not include things like, say, the power consumption of the memory chips, or the power consumption of the memory controller, or the power consumption of both. Really depends on the GPU. For example, on this card, if this card didn't have the shunts, it would not, or like if it didn't have the monitoring circuitry for the shunts, it wouldn't be able to report the power consumption of this voltage regulator, that one, or this one, or that one, or how much power the fan is using. So, yeah, and that, like, the main reason I point that out is basically if you try to compare software power readings from old AMD GPUs to NVIDIA GPUs, they're just not comparable, because NVIDIA GPUs, since the GTX 600 series, have shunt resistors so that they have accurate full board power measurements, whereas AMD GPUs don't until now. So now you actually get comparable power readings in software from AMD GPUs that you do on NVIDIA cards. Another issue is that even the power rails that AMD was monitoring, like say Vcore, which is the one that, like that's the one that they would consistently monitor because that one pulls the most power. So it's kind of important to keep track of it. But the problem with even the way AMD was monitoring Vcore is that the monitoring system that they were using was not really the most accurate. And so, yeah, that still wasn't great for like comparing the power, like software power readings on AMD GPUs historically have always been low, like inaccurate in the low direction, as in the GPU significantly underreported how much power it's pulling. With the RX 9000 series, that is no longer an issue. So yeah. Now then, let's move on to other functionality. We've got dual BIOS on this card. I have not bothered to check what the difference between the 2 BIOS chips on the card is. So I don't know, but I'm assuming one of them is supposed to be like slightly quieter than the other. I bought this card mainly for just chasing high scores in 3D Mark, so I don't really care if it gets really loud. And so like the default fan tuning, like the one thing I should have checked the BIOSes for is if there's a difference in the default power limit, but I kind of doubt it. Because the thing is, I bought this card because this was the cheapest option that I could find at the time that I was choosing a GPU, that I was like trying to buy a 9070. So I don't exactly have high expectations for one of these BIOS chips to have something cool on it. And also by default, usually cards typically ship on the performance BIOS, so that BIOS should have the highest power limit. So yeah, but anyway, so it does have dual BIOS. The main upside to having the dual BIOS is I do kind of want to mess around with flashing BIOSes from other GPUs on the card. And with dual BIOS, if that like goes wrong, as in you flash an incompatible BIOS, it's very easy to recover from that, because the way the GPU BIOS works is the BIOS chip is only read during the startup sequence. So basically, the way you deal with, like, if you have a dual BIOS card and you want to fix a botched BIOS, is like, let's say this chip is botched and this one's still good. Well, you boot off of the good chip. So the GPU will basically read what's in the good chip. It'll initialize itself with that information, and then it'll not try to commute, like, it will ignore that chip for the rest of the time. So once you're in the OS, you can flick over back to the botched BIOS and flash over it. So yeah. Anyway, so that's the like main upside to having dual BIOS. And technically, you can also like there's ways to do like recover bad BIOS flashes without dual BIOS functionality built into the GPU, but this is a lot more convenient than the alternative. So yeah, anyway, below the dual BIOS switch, we have the 5-volt regulator for the, like, primarily for the power stages. It might also power the voltage controllers. I'm not really sure, but the reason this 5-volt regulator is necessary is because the PCIe slot only provides 12 volts and 3.3 volts, and these two only provide 12 volts. So unfortunately, most power stages run off of 5 volts, and so if you want to have power stages on your GPU, you're going to need a 5-volt power rail to power them with. So that's what that is. Then on the back of the card, we have another 5-volt regulator. This one is a linear regulator, and this, as far as I can tell, is primarily for the 5-volt line in the HDMI port. Because, yeah, HDMI ports have like a 5-volt line in them, and so that regulator takes care of that. And it also has a fuse on it, because if you plug in something sketchy into that HDMI port, we don't want it breaking the card. Unfortunately, there's no other, like, you have fuses for protecting the display outputs. There aren't fuses for anything else on this GPU, unfortunately. Personally, I do like it when a GPU board, like, manufacturer adds fuses to the power inputs, because that makes the card more repairable for certain types of faults. But yeah, it's also kind of the norm to not bother with having any fuses. So, like, the ones on the display outputs are kind of a necessity, but for like the main power inputs, that's not really a thing. Anyway, moving on to other voltage regulators, we've got 1.8 volts over here. This powers the BIOS chips, and it powers the VPP rail of the memory chips. Next to that, we have 1.2 volts, which goes to the GPU core, and I don't know what it's for. I mean, I think, yeah, like... Nah, the memory chips only have 2 power rails. Those have VPP and VDDQ. So yeah, this goes to the core, and I don't know what it's for. And then we have this over here, which is another power, like, core power rail. This is 0.77 volts, also goes to the core, and again, I have no idea what it's for. I'm assuming one of these is probably primarily for like the PCIe interface, because that's like typical on NVIDIA GPUs, is you have something called the PEX rail, which, as far as I know, is called the PEX rail because it's for the like PCIe interface, as in the like actual PCIe lanes. Yeah, with AMD, I don't know what these rails are for, just that they go to the GPU core. So they're going to be powering some kind of minor circuitry in there. It could be like the display output circuitry or something like that. The thing that's like weird with AMD GPUs having all of these extra power rails is that the card already has a lot of power rails, as we're going to get to. So moving on from the minor voltage regulators to the big voltage regulators. On this side, we've got Vcore and VSOC. So the top half of this is Vcore. And below that, we've got VSOC. And then on the other side, we've got more Vcore. And then below that, more VSOC and also VDDCI. And this is my point about, like, man, AMD GPUs have so many power rails. So this right here is VSOC. and that's not very legible at all, so that's great. So I'll just put it on the inductor. VSOC, even though the active component in this is this. And then below that we have VDDCI, which is memory controller power. So, yeah, VSOC, more VSOC, and then memory controller juice. It's worth, I'm actually not sure how technically the PHY is, which is the actual, physical interface to the memory chips. That's why it's called a PHY, for physical. Is, wrapped around the GPU core. I don't know if the VDDCI rail is wrapped around the GPU core. It might be, but I don't know. It could be this is primarily powering the actual control logic of the memory controller, which wouldn't necessarily need to be strapped all around the core. All right, that could all be crammed in one corner and just controlling all of the outer edge. If it would even be doing that, I'm not sure. Not a actual GPU core architect, so yeah. Anyway, so VDDCI, VSOC, Vcore, and then up here we have memory power. And now we're going to get into how these are, and that's also not legible, so that's great. So yeah, up here we have memory power, and that powers the memory chips and, of course, the PHY, because the memory chips and the memory controller need, well, the PHY needs to talk to the memory chips with the same voltage that the memory chips are running on, otherwise things would get kind of complicated. So anyway, you'll also sometimes see this called VDDQ, and NVIDIA GPUs will typically call this FBVDD. Which stands for frame buffer. I just like calling it VMEM because these are memory chips. And this is the memory interface on the GPU. Anyway, so voltage controllers. We got two of them over here, and they're both MP 2868s from Monolithic Power Systems. This top one is running in a 4+1 phase configuration. The 4 is the Vcore VRM, because the Vcore VRM is running as a, it's running as a 4-phase, but with 2 power stages in each phase. So I'm not sure how I want to draw this. I usually try to do a dashed line, but that's just not super visible, so. Anyway, so these are, I guess I'll just circle them together. So yeah, these two are grouped together. And I know they're grouped together because of the current sensing circuitry being grouped together. That's actually how I figured out that this is a 4+1 phase, because at a glance, this really looks like it's probably an 8-phase. Yeah, no, it isn't. The controller, these 4 capacitors here are for actually filtering the current sensing lines coming into the controller, and there's 4 of them. And each of these capacitors is basically hooked up to 2 of these, for 2 of these power stages, as well as inductors, because technically, they join back up together at the front. But basically, the point is that the controller cannot distinguish between this chip and this chip. As far as the controller is concerned, these 2 are one big chip, and these 2 inductors are one big inductor, because, the current sensing circuitry for the 2 of them is shared, and the PWM signal going to them is also shared, right? So they switch on and off at the same time. And we've got the same exact thing going on the opposite side. So yeah, so that's the Vcore setup. As is typical for a lot of modern GPUs, we do have the split, Vcore VRM from both sides of the core. Though on a GPU of this tier, if this was an NVIDIA card, you'd probably expect all the Vcore power to just get shoved in from the bottom. Yeah, the idea behind splitting up the Vcore VRM like this is it effectively, and keep in mind I don't have schematics, so I don't know how the power planes actually look, but the idea is that since you're coming in from 2 different sides, you effectively get potentially double the cross-section of the power plane, which reduces the power plane resistance and also the power plane inductance, and that is good for power delivery efficiency. So, yeah, and I suspect the reason why the Vcore VRM is kind of weirdly high up on the board, right? You might be thinking, well, if we're trying to power this chip, why isn't it right here? I think it's because technically you have more space in between the memory chips over here. Right, because here you'd really have to, you're still going under one of the memory chips, but I think it kind of, like, my guess is that it works out better when you have this, like, gap in this area for shoving the power plant, like, for shoving Vcore through, instead of trying to run it directly under the memory chips, even though that's, like, typical for a lot of GPUs, but the workarounds for that would be, like, more PCB layers and that kind of thing, and that obviously would potentially drive up manufacturing cost. And also, if you have more PCB layers and you still use this layout, like, you still get the benefits of this layout, and now it's even better. So, yeah. So it's kind of, like, cool to see. And I'm just interested in, like, why it's kind of weirdly high up on the board. Because, funnily enough, on the back of the card, the Vcore capacitors extend all the way down to, like, here. So that, like, Vcore basically has to travel, like, you do have Vcore current, like, traveling all the way down to, like, there. Which does mean that you sort of get, like, slightly higher voltage up here than you get over here. That's, like, a very real thing with GPUs. Technically, it's also true for motherboards that, like, one edge of the CPU socket has slightly more voltage than the other edge. Yeah. Anyway, so 4-phase Vcore VRM with 8 power stages in it, so not anything particularly new. And the 8 power stages in here are monolithic power systems MP 87993s. These are 50 amp smart power stages. And unfortunately, they do not have a public data sheet. So for estimating their like thermal performance, I'm using the documentation for the MP 86992, which is also a 50 amp power stage, but the main problem I have with using this documentation is that these are in a 5x6 millimeter package, whereas these are a 5x5. So yeah, that's a bit of an issue. Like, usually if I'm using, like, different parts for estimates, I'd like to get them to at least be the same physical size. Not that that really tells us anything about, like, the thing is, the package itself might not entirely be reflective of the semiconductor inside the package, but, you know, I would have preferred if I could have found a chip from Monolithic Power Systems that was actually a 5x5 50 amp component instead of a 5x6, but yeah, they don't really make a lot of 5x5 parts, or at least they didn't used to. So like, all of the, yeah. But anyway, so I'm using the documentation for the MP. I don't know. Should I put this in I'll put it in, like, quotation marks. So yeah, MP 86992, which, looking at the part number, it might be a predecessor of the 87993. Like, maybe that was the actual development path, or maybe it's just, like, you know, depends on which year it was designed in, and they don't have anything in common with each other, which would be very unfortunate for me. Anyway, so yeah, let's talk about expected thermal performance for the power stages, and this is just the heat output of the power stages. This doesn't include power losses in the inductors or the power losses in the power plane itself, because that depends on what kind of power plane the board has. That doesn't depend on the power stages, and that can be a very significant thing. Like, I once tested a 4-layer motherboard with 90 amp power stages, and it ran like hot garbage. Literally, it was very hot. So anyway, let's go through this. 150 amps, which is probably a bit below the stock operating current. Oh, and this is 1.2 volts output voltage, which is high. So if anything, the thermals should be a bit better. Well, the funny thing is that 1.2 volt output voltage is at the inductor. So depending on how much voltage drop there is across the power plane, this might actually be relatively accurate, right? Because the GPU core might only be getting 1.023, like 1.03 volts-ish, something like that. But that doesn't mean the VRM isn't outputting almost 1.2. Though on a GPU, I wouldn't expect it to be that bad. That's more of like a motherboard thing where you get, like, a huge difference between the voltage that the chip actually gets versus the voltage that the voltage regulator is outputting, because CPU sockets are very high resistance compared to BGA devices. But anyway, so assuming 1.2 volt output voltage, 500 kilohertz switching frequency, at 150 amps, this VRM should produce about 12 watts of heat, which is very, very good. So yeah, that's, like, amazing efficiency right there. But that is also, again, just the power stages. And then 200 amps, the power stages should be producing about 17 watts of heat, which is also just very good efficiency again. And then this is probably pretty close to stock operating current for this core. Well, I think that would be probably closer for the 9070 XT than the 9070, but this PCB gets used for both. Or like, yeah, like this PCB is basically a reference PCB for the 9070 and 9070 XT. So there's quite a lot of like the cheaper cards will generally use this PCB with some minor modifications. Anyway, 250 amps, about 24 watts of heat. And now at this point, like the thing is, this is not a lot of heat relative to how much current this is outputting, but it is kind of a lot of heat relative to how many power stages we have, right? Because there is only 8 of these, and so this is actually 3 watts per power stage. Now, it's not really a problem on a GPU because GPUs have fans on them. So that's one of the like interesting things that you might have noticed is like motherboards, in order to achieve good VRM thermals, need absolutely giant voltage regulators, and GPUs can get away with much more reasonable like VRM configurations, because with GPUs, the designer of the board knows for like with absolute certainty that the GPU is shipping with a VRM heatsink that has direct airflow. Right? So you don't like this is very efficient, but 3 watts per power stage is actually quite a lot of heat in terms of like thermal density. So 3 watts per power stage on like a motherboard would generally be not great for thermals. Whereas on a GPU, it's really not a big deal. Also, to pull this much current, you need to actually disable the card's power limit. So not really a concern for stock configuration. 300 amps output current, the power stages will probably produce about 34 watts of heat, at which point, yep, that is getting into actual problem territory, right? Because this is over 4 watts of heat per power stage. But luckily, this is probably only going to occur if you're pushing the card to the limits in short benchmarks. Then 350 amps output current, the VRM will produce about 45 watts of heat, which, like, now, like, this is where I'd be, like, this is probably, like, LN2 overclocking territory, and at this point, I'd be concerned for the health of the VRM, this is what this is, because that is quite a lot of heat. Like, it's not going to instantly overheat and die. And these are smart power stages, so they do, or at least they should have built-in over temperature protection, and it's hopefully enabled. Yeah, at this kind of output current, I would like really, think about how the VRM is being cooled. Though also this is not really going to be something you're going to run into in day-to-day scenarios. And then 400 amps output current, which is completely maxing out the power stages, right? Like these are 50 amp parts nominally. The VRM would kick off about 60 watts of heat, which is going to be very difficult to cool. Now, what's worth noting is that both of these figures like in order to reach these, you need to like modify the card, because like the first thing is that generally the card won't really be able to pull more than 250 amps anyway. But if you do manage to push past that, well, no, because if you use the stock power limit, you won't. Like, you have to modify the card to bypass the power limit. But if you had like a 9070 XT, the VRM still, like, the card still has a 330 amp current limit, which is like right here. So, which is in between that 300 and 350 amp figure. So you don't really have to worry about maxing out the VRM on these. So yeah, and the funny thing is, like, admittedly, I am using numbers for the MP86992, not the MP87993. But I would hope that the newer part matches the performance of the old one. Or at least, yeah, like at least matches the performance of the old one. So yeah, even though this is like the most basic VRM configuration you can get on a 9070, I don't really have any problem with it. So yeah, I think it's perfectly adequate in terms of output current handling capability. And what did I want to mention? Oh yeah, also for like higher end 9070s and 9070 XTs, what you'll usually see is that the MP86 2868 over here, instead of running 4+1 with 8 power stages, it just gets run as a 5+1. And as far as I can tell, I think this controller actually maxes out at 6 phases. Because I've not seen a 9070 or a 9070 XT with more than a 5-phase configuration for the Vcore VRM. Because the way this controller is set up is that the 4 is Vcore, and that +1 is VDDCI. So, yeah, and so VDDCI is memory controller power. This is a relatively low current rail. It's also a rail that even when you're overclocking doesn't really, like the amount of current that this is going to be outputting doesn't really change. So we don't really have to worry about it because it uses the exact same 50 amp power stages that the Vcore VRM uses. So that's cool. And then VSOC is VSOC is a 3-phase running off of the second MP 2868 that we've got over here. And this is running in a 3+2 phase configuration, so that's SOC plus VMEM. And we've got more MP87993s for that. So, yeah, I mean, I wouldn't call it a 150 amp SOC VRM, because again, you run into that problem of like when you max out the power stages, they get awfully hot just because of the thermal density that they're at. And as for how the SOC power rail scales with overclocking, I don't know. I haven't tested it enough yet. But well, on the 6900 XT, this power rail basically didn't do anything, and like it didn't well, okay, I shouldn't say it didn't do anything, but it didn't like see drastic power draw increases like what you get on Vcore usually. So yeah, I wouldn't be concerned about the VSOC configuration whatsoever. Yeah, also you can see that there was the option to run the second MP2868 as a 4+2. And they didn't do that because it's just unnecessary for the SOC power rail to have 4 phases. So, yeah, that's the power stage and phase configuration. It's not the most overkill thing ever, but, you know, I was buying the cheapest 9070 I could find, and then my purchasing process was, I want the cheapest card, and I want the heaviest heatsink, because there isn't, like, that's like the annoying thing with the base model GPUs, is there's not usually a lot of reviews for them. So it's like, I want the best heatsink for the least money, because I'm not going to get a good PCB, because those are expensive. So I just bought the heaviest, cheapest card I could find. And that's how I ended up with this thing. So, yeah. And in terms of VRM configuration, like, I am pretty happy with it. Especially considering the fact that, like, the next step up in terms of PCB is just you get a 5+1 instead of a 4+1, and you get 2 more of these on most cards. Technically, the ASRock Taichi actually upgrades the power stages themselves, but most cards just go from 4+1 to 5+1 and 10 MP87993s instead of just 8, which isn't really that much of an upgrade. Anyway, so yeah, current handling, current and like power handling capacity wise, I like this. Now then, capacitors. This is where I am not a big fan of what XFX has done. Input filtering is good. We've got one big bulk cap over here for the PCIe slot. Then we've got these 3, and I think this one, I'm not sure. I should have probably I should have measured this when I had the card taken apart. But basically, like, the thing is, we have 4 capacitors right here, and then this one. And then we have 3 over here. And the way the card is wired is this 8-pin. Actually, I'm not sure if it's this 8-pin or this 8-pin. But one of the 8 pins basically powers this entire side of the card. And the other 8-pin just powers everything on this side of the card. This is also, if you're thinking about like removing the power limit from the shunt resistors, there's no reason to mod the PCIe slot, because this literally doesn't power anything. Okay, that's not true. It powers this, and, you know, this. But those don't matter, so... doesn't power anything. So Anyway, but because the two 8-pins are basically split between one side of the card and the other side of the card, I'm assuming that this side has, 4 capacitors, like that both sides of the card have 4 bulk capacitors for it, and it's just that the one, like the fourth one for this side of the card is this one or this one. I'm not sure. Anyway, what's kind of funny is that this 9070 has significantly more bulk capacitance on the input than a reference 6900 XT, I just kind of find that funny, mostly because it's like the 6900 XT has like a weirdly low amount of bulk capacitance on the input. So, but anyway, yeah. So as far as bulk capacitance concerned, there's plenty of it, I think. Bulk input capacitors, in my experience, don't tend to do much for output filter, like for voltage regulation to the GPU core, because your bulk capacitors are behind the inductance of the inductors, right? So I don't really consider them like performance critical components. And so having 8 of them for a card like this, I think is perfectly acceptable. I mean, technically it's 9 because this one exists, but like I mentioned, it doesn't really power anything that matters that much. So yeah, like the main power rails have like 8 bulk capacitors for them. Now, what I'm much less happy about is the output filtering. Because from the front, it's fine, right? We're missing one capacitor on VSOC. I don't really have a problem with that. The SoC power rail probably isn't that noisy. I haven't measured it, but I've measured it like VSOC. I've measured it a couple times on other GPUs, and it's generally pretty quiet. So I'm going to assume that the 9070 didn't drastically change things there for now, though I will try to measure that eventually. Because, yeah. But the fact that they decided to leave out one of the cheap bulk capacitors is like, okay, this probably doesn't matter that much. VDDCI, I also don't really see anything wrong with that. We've got 2 bulk capacitors, 820 microfarads, 2.5 volts. I mean, these are all the same capacitor, right? Like, I think you've noticed at this point, the markings on all of these are exactly the same. So yeah, these are all 820 microfarads, 2.5 volts, solid polymers. Don't know who makes them though. I don't recognize these markings, so I don't know what brand they are. But they're solid polymers, so in my opinion, it doesn't really matter that much. Since, like I've mentioned in past videos, solid polymers are borderline indestructible unless you do something really wrong with them. Anyway, VDDCI also has this extra, what I'm suspecting is a Panasonic SP cap on it, 470 microfarads, which I find interesting because I wouldn't usually expect the VDDCI power rail to require extra, like, power filtering, but yeah, apparently it does. But no, my main complaint for this card in terms of capacitors is the Vcore power rail, because what you'll notice looking at the back of the card is that there is an awful lot of unpopulated capacitor pads, both like bulk ones as well as like smaller multi-layer ceramics. Basically, and you know what, I guess I shouldn't really complain, because at the end of the day, I did buy the cheapest card with the heaviest heatsink. That was kind of my purchasing criteria, so I don't know why I expected to get a full complement of capacitors, but yeah, XFX basically, like, any capacitor that isn't absolutely necessary for the operation of the card is just not present, right? Like, even the little multi-layer ceramics for input filtering, like, they left one out. And I think these ones are the ones directly behind the power stages. So there is... Oh, and then we have like extra bulk input filtering over here, but those don't matter. So these I don't care. But the output filtering ones over here and just, well, everywhere, right? Like, look at all of this. Or like, look at how all of this is missing. Actually, technically this is VSOC. But yeah, so all of this on Vcore, like, it's just not there. I am not a fan of that. Yeah, because I have already hooked up the oscilloscope to the card, and it is pretty noisy. So, yeah. But then again, I did buy the cheapest card with the heaviest heatsink. I don't know why I was expecting to get all of the capacity, Well, I wasn't expecting all of the capacitors, because even some of the, like, high-end 9070 XT PCB designs will have a bunch of unpopulated capacitor pads, but it's not this empty, right? Like, this really is, like, they just didn't populate anything that wasn't necessary for the card to function. So I am not impressed by that. And as far as I can tell, the Vcore VRM has 10 820 microfarad, 2.5 volt solid polymer capacitors. And that's it. And then there's like some multi-layer ceramics that they left. So yeah, not a fan of the bulk capacitor configuration. And honestly, even like the little multi-layer ceramics for like at the output of the VRM, like, yeah, they're also just not populated. So not super impressed with that. What I did find really interesting actually when hooking up the oscilloscope to this card is, as far as I can tell, this entire row, and actually all of these rows of multi-layer ceramics behind the core, are same side polarity. So, and the reason I bring, and what I mean by that is that, like, this side is, yeah, I think this is the positive side for this entire row. So you'll have like plus on this side for this entire row, and then minus on the other side. And the reason I bring that up is, as far as I know, if like there is an like there's a inductance or like PCB inductance optimization that can be done with small decoupling capacitors behind big chips like this, where you intentionally have them in an alternating pattern. So you'll have like minus, plus, plus, minus, minus, plus. You get the idea. Now, obviously, the reason you wouldn't do this is this adds like a bunch of complexity to the board design. But this is actually a pretty typical setup on NVIDIA GPUs. Is that like if you poke around the little multi-layer ceramics on an NVIDIA GPU, a lot of the time their polarity is just all over the place, and it's horrible when you want to hook up probes, because you can't just, you know, like, on one hand is very convenient for hooking up the oscilloscope, because I can just connect the probe to like 4 capacitors at the same time and it's all good. Right? I don't have to worry about shorting anything out because they're all the same thing on the same side. But on the flip side, it is like, yeah, that is interesting that AMD doesn't bother with that, like, layout optimization. Though I don't know how much of an effect it has on the actual, like, power delivery at the GPU core. So, yeah, this is more like, I'm not like, this isn't really meant to be a critique, more of an observation of like, oh, that's kind of interesting, because I was honestly expecting this to be alternating polarity multi-layer ceramics, and it's instead all the same side, which kind of surprised me. Anyway, so that's the Vcore setup on this. So also XFX has no control over this part. This is the layout of this is controlled by AMD. Though I think on some past GPUs, occasionally you'd get like some variety of how the capacitance value of these multi-layer ceramics, though I don't think with the newer cards that the board partners would be able to play with that. Though usually the only board partner I've ever seen really fiddle with that is like Asus. Like, you'll find some, like, yeah, you'll occasionally get like Asus cards where everybody else uses like a 22 microfarad capacitor behind the core, and Asus uses a 47. So, yeah, which can slightly help with like core power delivery. But anyway, let's move on to the memory power delivery. Now, the memory power delivery has me basically as disappointed as the Vcore power delivery, though it is worth noting that with the memory power delivery, if the memory, like if the power supply to the memory chips isn't the bottleneck when pushing the memory frequency, which basically what I mean by that is, like, if the, like, let's say I want to run the memory at 2900 megahertz, right? Which definitely won't work. My card maxes out at around 2820, depending on what benchmark you're running. But let's say I wanted to run it at 2900. It might be the memory controller that can't run 2900 megahertz. And if it's the memory controller that can't run that frequency, then more power filtering for the memory chips is not going to do anything. So, yeah, that's kind of something that, you know, needs testing on my side. But, yeah, the memory power rail on this is like, okay, so we've got our 3 bulk capacitors. But what I find kind of insane is that they've just left out multi-layer ceramics everywhere, which is really quite strange to me. Because it is pretty typical that you will, like, like that you'll want to have some like bigger capacitor near each of your memory chips, and it's just like, no, only little ones. The big ones apparently cost too much. So, yeah. Now, the bulk capacitors that are present are 470 microfarad SP caps, as far as I can tell. And so those are really good. Like these are basic. If these are Panasonic SP caps, these are easily my favorite type of like polymer capacitor. Because these have just amazing equivalent series inductance and equivalent series resistance. These can rival the performance of large multilayer ceramics. But yeah, there is only 3 of them, and all of the all of the larger multilayer ceramics were not populated. So I'm assuming that the reasoning behind that is hopefully that it's just like, oh, the memory controller can't actually do high frequencies and not capacitors cost too much. But that is something I do want to mess around with, is like populating all of these pads to see if maybe I can't eke out higher memory clocks, though. That's usually been a thing for me on like NVIDIA cards. Rather than AMD GPUs. Like, I don't think I've ever had an AMD GPU clock memory higher after adding extra capacitance to the memory power delivery. I have had that happen with NVIDIA cards, though. Because NVIDIA cards have, like, the way their memory controller is powered is very different from how AMD powers the memory controller. And so NVIDIA GPUs actually put a lot more stress on their memory power delivery than AMD GPUs do. But anyway, and I think that covers everything. No, I forgot to point out J40 4003 over here. XFX has very kindly labeled the I2C hookup. So if you want to hook up something like the Elmore Labs EVC2 to take full control of the voltage controllers on this. Actually, I don't think the controllers on this are supported just yet, but I imagine Elmore is working on that. And there is some support for the controllers as of right now already. But yeah, you can just hook up to that, which is very convenient. Also, I want to point this out. If you're modding AMD GPUs, this header is very common, even on custom boards. Like, I know I mentioned earlier, like, this seems to be a bit of a reference PCB for the 9070 XT. But, like, this header label is consistent even for custom cards. A lot of the time. Like, I'm not sure every time that it's always J4003, but like I checked a few custom 9070 PCBs and you can find J4003. So there's really, and the reason I bring that up is I've seen people solder their I2C hookups directly to the voltage controllers, which is just, why would you do that when there's a conveniently, I mean, on this card it's convenient, but on most AMD GPUs, there is a J4003 header somewhere. And I think on some of them it's like J4004. Like, it's a J4000 something header. Just hook up to that. And then you don't have to deal with soldering to tiny little, pins on the controller. Because the worst part is if you, like, even if you do manage to attach your wires to these, if you put a little bit too much stress on those wires, you are going to rip traces out of the board and you're going to have a very bad day. Because AMD GPUs get awfully upset when their I2C interface gets disconnected from the controller. So, yeah, and I think that covers everything. Yeah, I pointed out the I2C header, complained about the lack of capacitors. Yeah. That's the XFX 9070 Swift OC PCB. I will have a video about how to physically remove the power limit on this card in the future. And as well as like modifications and other things with this card as well. I've already removed the power limit on mine, so yeah. You can look forward to that, I guess. And that's it for the video. So hopefully you found this somewhat interesting, if not particularly useful. And thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions, comment stuff in the comments section below. And if you'd like to support the channel, there are links in the description. If you'd check them out, that would be very much appreciated. And that's it. So thanks for watching, and goodbye.